In the last video, we finally introduced thermodynamic entropy. In this one, we're going to learn how that applies to our first control operation, which again we called adiabatic work. But before we can do that, we need to discuss a couple of concepts that apply to the control operations and to simple systems as a whole. The first one is equilibrium. So thermodynamics, classical thermodynamics, is a theory that involves systems which are at equilibrium. But what does equilibrium mean? We can now give that a sort of definite answer within the theory. Again, the state space for a simple system, which we've been calling gamma, will look like this. It'll have one internal energy coordinate and then a bunch of work coordinates, which I'll call V1 through Vk. The key is that each of these coordinates should be well defined in the sense that it describes the system as a whole, and should not vary in time. So why does, for instance, our ideal gas system meet these criteria? Well, this system is described by the three coordinates u, v, and n. If we do nothing to the system, it will remain in equilibrium. That means that its internal energy, which again we said was the sum of the kinetic energy of all of the particles, will stay the same. The reason that that is true is because, well, conservation of energy applies here. The system isn't losing energy because it's isolated from the outside world, and so its internal energy will remain fixed through time. Secondly, the volume will not change if we do nothing to the system. That's because it's just in a closed box. Finally, the number of particles won't change either if we do nothing to the system because the particles are constrained by the walls of the box. Okay, but we do want to be able to make some changes within our theory of thermodynamics. We just want the user to be the one who creates the changes, who causes the changes. So what kind of restrictions must there be on the kinds of changes we can make to thermodynamic systems? And the answer is that at every point in the change, all of these variables should stay well defined. Let's give an example and a counterexample. If we change this ideal gas system by expanding the box out slowly, then at every point in time, the volume, energy, and particle number will be fixed. So this is sort of the normal case that happens if we do this expansion very slowly. However, for a counterexample, look at the alternative case. Suppose we expand the box out very quickly, such that the particles inside of the box don't quite have time to reach the new left-hand side of the box as I'm drawing it. In other words, there will be a moment in time when this side of the box is empty. In this case, a question arises. What is the volume that's relevant for thermodynamic processes? Is it the volume that the particles are still occupying or the total volume of the box? In fact, we just sort of don't have a good answer to the question. And so this isn't a case in which thermodynamics provides a good model for something that can happen in reality. We would have to use something like classical or quantum physics in order to model the system more completely. So we're going to restrain our sort of focus in this course as we focus on classical thermodynamics to these processes that happen slowly enough that all thermodynamic variables are well defined at every point in time. Such a process is called quasistatic. So, when we go on to talk about control operations, what we should remember is that the system at every point in time is in equilibrium. When we make changes to it, those changes are quasi-static so that the system maintains all of its thermodynamic variables constantly over its whole spatial extent at every point in time. With all of that, we're now ready to talk about our first control operation, which is adiabatic work. Adiabatic work operations are ones that we can do to a system that leave its entropy fixed. Gonna make me nuts. Okay, here's a good example. Suppose we take one of our boxes of gas again. This time, instead of expanding the box, let's compress it. So we'll apply some force to the box to push it in. Notice that this is something that we can do coarsely. We talked about coarseness of work in an earlier lecture. And that's important. We can't manipulate the individual atoms here. We have to do some sort of coarse work to the box. But if we do this coarse work slowly, we do some work in order to push the box in, since the gas particles will be creating pressure inside of the box that takes us some effort to overcome. So after we've forced the box in, we can have changed its internal energy. And so we can do some sort of work that leaves its entropy the same. Let's figure this all out using the ideal gas model. So again, for the monatomic ideal gas, we have that the entropy as a function of u, v, and n is equal to n kb times the log of phi v over n u over n to the power of 3 halves plus 5 halves n kb. Now, if we want to increase the energy of the particles inside the box while decreasing the volume in a way that keeps the entropy fixed, we see that there must be a relationship between u and v. In particular, let's say that we reduce the volume of the box. Let's say we reduce it in particular by half. So I'll say that S of u prime, which we don't know yet, 1/2 v n, well, that'll be equal to n kb log phi v over 2n u prime over n to the 3 halves plus 5 halves n kb. And if we want these two to be equal, then we're going to need to calculate what u prime must be. We'll need to calculate how much work we'll have done to the box in order to make this happen. So in this case, let's look. We'll need this 1/2 to cancel something coming from u prime. So u prime must be related to u in a particular way. We must have u prime to the 3 halves equal to 2u to the 3 halves. And then if we take the 2/3 power of both sides, we find that u prime must be equal to 2 to the 2/3 times u. So we must have some sort of very careful relationship here that allows this to be true. How can we make this happen in the lab? It turns out that adiabatic changes are typically even slower than quasistatic changes because they leave the entropy fixed. As a good rule of thumb, entropy tends to increase when we do processes faster or more violently, and tends to not increase tends to increase less, at the very least, when we do processes more slowly. That's not necessarily something that the theory of classical thermodynamics can always model, but it does turn out to be true. Okay, so I think that that's enough on adiabatic work to get us going. In the next video, I'm going to want to hop and talk about joins, which are going to be our other form of control operations. Until then, I'll see you in the next one.